Hi everyone, my name is Luca Marzari. I'm a master student in computer engineering at University of Verona, and today I'm going to present our work titled Curriculum Learning for Safe Mapless Navigation. Okay, let's start with a brief introduction and related works. In the recent year, deep reinforcement learning has shown success in various fields such as games, robotic manipulation, and especially autonomous mapless navigation tasks. However, deep reinforcement learning is a data-hungry training regime that requires millions of trial-and-error attempts, and even if we reach a nice success rate in the training or testing phase, this does not imply that our agent is always safe. So, in this work, we propose a deep reinforcement learning framework to reduce the training time and increase the safety in a mapless navigation scenario. To this end, we consider a scenario where basically we have a robot positioned in a random point on the map without global knowledge of its surrounding. The agent locally scans the environment with a 360-degree laser scan placed on it, and its goal is to reach a random target position in the environment. For this work, we decide to use the Robotnik Kairos mobile robot as an agent, and we create both the training and the testing environments using Unity, in particular ML agents, for the communication between the environment and our agent. The mapless navigation problem is a widely adopted benchmark for robotics research due to its practical implications. A line of research employs supervised learning approaches where human intervention or demonstrations are used to collect data from a realistic scenario to help the agent learning phase. However, this research trend requires imaging processing, resulting in computational demanding solutions. In contrast, the typical trend in robotic research employs policy gradient or value-based approaches thanks to the possibility of accurately model joint velocity in robotics. So, following this direction, we introduce a deep reinforcement learning framework to reduce the training time and increase safety. And in particular, we investigate the effects of curriculum learning-based approaches combined with transfer of learning or fine-tuning techniques on the agent performance, in particular focusing on the safety aspect. Moreover, to further confirm the results obtained empirically, we employ Prove, our formal verification tool, to quantify the number of correct behaviors of reinforcement learning policies over desired specifications. Before diving into the methods, there are three key ingredients to consider for the methods used in this work. The first one is the concept of curriculum learning that is presented as a new training paradigm where basically we gradually increase the complexity of the task during the process of learning. The second one is the concept of transfer of learning, typically used in machine learning scenarios, where a model trained for one task is used as a starting point for the learning process of a new related task, using freezing action between the two training phases. And finally, for each method that I'm going to present, we use PPO with discrete action spaces as a deep reinforcement learning training methodology. Okay, let's start with the methods in detail now. And we start with end-to-end methodology, where first of all, we create a final environment called final emp, with challenging difficulties for navigation, such as narrow corridors and U-shaped walls. In this environment, we start with an end-to-end training in an uninformed fashion, so without any type of prior knowledge about navigation, to see how many steps are required to get a constant high success rate. As we can see in this plot reported here, the steps in this room required to get an success rate are 6 million. So following the curriculum learning insight, we split these steps into smaller ranges for each sub-scenario, trying to create an increase in difficulty. For a fair comparison, all the methodology are trained with the same number of final steps. So, as we can see here, in order to build an increasingly informed knowledge about navigation, for the curriculum learning with transfer of learning technique, we start from the basis of navigation, basically an empty room with only two obstacles placed inside it, and for this room we set a limit of 1 million steps. For each new environment provided to the agent, the difficulty and the number of steps allowed increase. Once we reach a high success rate or the maximum steps allowed in one room, we dynamically load the next one, and before starting the new training, we freeze one of the remaining 3 hidden layers. Fine-tuning is the same of transfer of learning, but without the freezing action between one and another environment. Okay, let's see the results. These are the results for the training phase. The plot depicts the comparison between the end-to-end and the transfer of learning methodology. Each peak represents the maximum success rate reached by the agent in each sub-scenario for the transfer of learning methodology. The data are collected over different runs with random seeds. We can notice that when the agent trained with transfer of learning starts the training in the final environment, so after 3 million steps, immediately achieves a success that exceeds the one of end-to-end, and this is probably due to the knowledge acquired in particular on the second int-emb, which allowed the agent to acquire more skill, in particular on making longer but safer trajectories. In general, transfer of learning shows better performance than end-to-end. The testing phase is performed on 5 new unseen environments beside the one where we train the robots. These new scenarios all have similar characteristics to the final emb, and we consider as a metric of difficulty the area occupied by obstacle and the minimum distance between 2 obstacles in the environment. The bar plots represent the success, the collision rate, and finally the average distance performed by the agent for each environment tested and for each methodology. In particular, in the table reported here, we show the average gain in terms of safety, measured here as a collision rate, in using transfer of learning or fine-tuning techniques with respect to an end-to-end methodology. In general, transfer of learning can have better adaptability to unseen environments, achieving high success rate and safety level. To conclude this presentation with the formal verification part, let's recall some notation. Following the formulation provided by Liu et al., a safety property can be written as reported here. In particular, in this form, we aim to verify if an output of a network lies in a specific interval given a particular configuration for the input space. This formulation can be applied to many problems related to robotics and deep reinforcement learning. However, it requires to manually modify the input space, introducing overhead in the verification process. In contrast, we propose a different formulation designed specifically for decision-making problems. We refer to this formulation as safety property for decision-making, as it can be used to ensure that a particular action is always preferred over other actions for a given input configuration. In order to check if an action is preferred to another one, we use the interval algebra of Moore, in particular the relation reported here. So, given a particular safety property written at high level as reported here, we translate it into a mathematical notation and we investigate if an agent behavior is correct. So, in other words, we check if, given a particular input state configuration, the actions selected are correct and safe. So, we reported here the results of our formal verification. In particular, we design a set of 5 high-level properties that describe the agent behaviors to ensure that it makes rational decisions. In the table reported on the right, we show the mean and the standard deviation of the violation metric. So, how many times in percentage the agent violates a safety property for each property and for each method presented. The formal analysis of the training network confirms that overall transfer of learning is the safest approach with the lowest violation rate. So, thanks for your attention, and the source code of this work is free available at this link or scanning the QR code, and if you have any question, please write me. Thanks.